Proof of Sylvester's law of inertia. Recall the theorem from the last video. We started with two diagonal matrices A and B of the same size that were congruent to each other, that is, B equal to P transpose A times P for some non-singular P. Then the number of positive entries of A must match the number of positive entries of P. Similarly, number of negative entries and number of zero diagonal entries must also be same for A and B. Let's take an example. If A is a diagonal matrix 4 by 4 with diagonal entries 100, -5, 2 and 0, then it is possible for B to be something like this, where the number of positive entries here is 2, the number of positive entry here is also 2, the number of negative entries is just 1, here also it is 1, and number of zero entries is also 1. Observe that the positions may be different, the actual values may be different, but the number of positive, negative and zero entries must match. For instance, it is never possible to have something like this, because here the number of positive and number of negative entries, they do not match. The proof is actually quite straightforward. First, observe that since we are working with diagonal matrices, the number of non-zero entries, positive and negative both put together, that will give you the rank of the matrix. For example, this matrix has rank 3 and this also has rank 3. Now, you are obtaining B from A by pre and post multiplying by non-singular matrices. Remember, if a matrix is non-singular, so is its transpose. Now, multiplication by non-singular matrix does not change rank. So, rank of A is same as rank of AP, which again is same as rank of P transpose AP, and that is our B. So, we see rank of A must be rank of B, and from this we immediately conclude that the number of non-zero diagonal entries must match, because that is the rank. Now, since both of them are of the same order, so you immediately get that number of zero diagonal entries must also match. So, that part is settled. So, now we have to figure out whether the number of positive entries match, because that will immediately say by elimination that the number of negative entries must also match. Now, let us attack the problem from the other end. Suppose I give you a diagonal matrix like this. Can you quickly give me another diagonal matrix which will be congruent to this? Now, one type of diagonal matrix that is guaranteed to be congruent to this is obtained by simply permuting these numbers like this. I just permuted them. I could have taken any permutation. What I did, I just cyclically shifted them. So, 4 came up and 1, 2, 3 got shifted down. Now, I can say that this must be congruent to that, and this I can do in a constructive way, because all that I have done is basically I have permuted the rows. In this way, 4th row comes in the first position and every other row comes down, and then done the same thing for the column. That is why the diagonals remain in the diagonal. Now, whenever I do this, namely permuting the rows and columns, I can implement that by pre-multiplying and post-multiplying by a permutation matrix. To just construct that, I will consider this permutation matrix. I will start with the identity matrix. And then I will do exactly what I want to do here, namely I want to cyclically permute the rows. So, what I will do is I will take the last row up there and shift everything one place down. So, I will start by shifting them down. This one comes here, this one comes here, this one comes here, and this one goes up there. So, I get a permutation matrix which is of course non-singular, it is actually an orthogonal matrix, and I call that P. If I do that, then if I pre-multiply by P, then this 4 will go up there, the others will come down. And if I now post multiply by P transpose, well, the way I wrote it earlier, I should better call this my P transpose because I am P multiplying by this. So, and that will be P. It will implement the same thing in the columns, and that will give me this particular thing, which means that I can always permute my diagonal entries whichever way I like without going out of the same congruence block. If I permute, the resulting matrix is always equivalent to my original matrix. So this gives me some flexibility in terms of assuming where the positions of the positive entries and negative entries, etc. are. Now let's get back to proof of Sylvester's law of inertia. So I have already shown that if two matrices are congruent, then their number of zero diagonal entries must match. So here I have given you two such matrices, same order, and number of zero diagonal entries is equal to 1 in both cases. However, I have deliberately chosen a case where number of positive entries do not match. Here it is 3 and here it is 1 and 2. So number of positive and negatives do not match. So I shall try to prove Sylvester's law of inertia, whatever remains of it, by contradiction. So I will say, if you give me two matrices where number of zeros anyway must match, but if the number of positives do not match, then they cannot be congruent to each other. So we are going to use proof by contradiction. So I shall show as an example that these two things cannot be congruent, and the argument that I shall be using will be general. Okay, so I have already seen that I am free to permute these things. So what I shall do is, I will say I will first permute these things to bring all my positive entries to the top. So I can do that. So here the entries were 1 minus 2, 2, 0, 3, minus 6. So 1, 2 and 3 are positive entries, bring them to the top, and then write down all the negative entries. They were minus 2 and minus 6. So I bring them here and the 0 is at the end. By doing this, I am still in the same equivalence block, I mean the same congruence block as my original matrix. So if I can show that these and these cannot be congruent to each other, still I have shown what I wanted to show. So most books just write this step in a single line without loss of generality. Assume that all your positive entries are in the leading position. Well, I will do the same thing here. In this case, my entries are minus 2, 39, minus 1, 40, 0 and minus 10, of which only these two are positive. So I bring them first. Then I have got 3 negative entries. They will come after that. And finally, the 0 entry. So I shall show that these two matrices cannot be congruent to each other. So let, if possible, we have some non-singular matrix P such that I have this. Let, if possible. I am going to show this will lead to a contradiction. So P is some non-singular matrix. The way we shall attack is by focusing our attention on this particular entry. This seems to be the only extra positive entry. Forget about the negative entries for the time being. What I shall do is, I shall try to find a suitable vector such that if I call this matrix A and this matrix B, then my suitable vector should have this property. I will pre and post multiply by x transpose and x here and also do the same thing there. Since they are equal, they will also remain equal. Now, x is a vector, so is this fellow. Suppose I call this vector y. So this is y transpose. Now, my suitable vector will highlight this entry in the following way. What I will do is, I will make sure that the first two entries of x are 0. So these two things cannot play any role. So x must start with 2 zeros. And then whatever. So when I do this, you can see I will be only working with the negative and the 0 entries. But I will choose my x in such a way such that px, this y, will have all these entries equal to 0. That is, the last 3 entries of y will be equal to 0. I am not saying that I can get such a thing, but that is what I want to get. Now observe that if I can get such an x where the first 2 entries are 0, and when I compute px, the last 3 entries are 0, immediately my proof is done. Because I have first 2 entries 0, this quantity is bound to be something which is non-positive, because these two things cannot give any positive entries. On the other hand, because these things have been ruled out, this must be non-negative. But still that is not a contradiction. Now you observe that this fellow is strictly positive. So one of them is a non-positive and the other must be strictly positive, and immediately my proof will be over. So the only thing that I have to do is to find an x such that the first 2 entries here are 0 and the last 3 entries here are 0. Question is, can I really get such a 6-dimensional vector? Now, it is quite easy that we can actually get such a 6-dimensional vector simply because I am trying to get x which satisfies these equations. First of all, x1 must be 0 and x2 must be 0. They are simple. Then I am considering y 1, 2, 3, 4, 5, 6 should be 0. So y4 must be 0. Now what is y4 by the way? Y is p times x. So if I consider its fourth entry, it is nothing but the fourth row of p times x. I have called the fourth row p4 prime because it's the row vector times x. That is 0. This is 0. This is 0. I do not care what these things are. I can see that this is a vector which is, this is a system which is a homogeneous system. So it is bound to be consistent. And how many restrictions do I have? 5. Which the number is less than 6. So I have got 6 unknowns and only 5 restrictions. Whatever those restrictions are, obviously they cannot be contradictory. It will always be consistent because it is a homogeneous system. So I can always solve such a system, and not only that, I can get a non-zero such vector. And that is what will guarantee that this will be strictly positive, whereas this would be non-positive. So I can always get a non-null vector x which will satisfy all these conditions because there are 6 unknowns and only 5 restrictions. And that shows that it is always possible to do this. Now you might think that I am doing it only for the special case, but don't worry, it is actually general. In general, it will be of length n, and you will have some restriction here and some restriction here, but remember there is something which is left out. Those are precisely the things which are positive here but not positive here. So because I am leaving out something, so the total number of restriction will be always a bit less than total number of unknowns. So this argument will always hold, and that proves Sylvester's law of inertia.